one visiting critic, fourth-year studio that has been staffed by a firm in Chicago. This year is no different. In the spring quarter, one of the fourth-year studios is that of a team from SOM. Craig Hartman is with us tonight. He represents that team. He's a 1973 graduate of Ball State, and he's one that I think everyone here who happened to have him in the studio is very proud to have back with us as a faculty member. So with that brief intro, Craig Hartman.
Well, it's a pleasure to be back to school. I'm not so certain that my fourth-year students necessarily share that opinion, but it is great to be back. I think in the last few years since I've been away from the school, a lot of positive things have transpired. The quality of education, the quality of work that I've seen since I've been back has continued to be very high. And likewise, with the new addition going on to school, I think that we all have, as Ball State graduates, have a lot to be proud of. Likewise, at SOM in the last few years, there's been substantial evolution that's occurred, I think, both in the design philosophies in terms of more diversity and inclusiveness in the approach to design, but also in the technical resources that we have in the office. I think particularly in the last 3-4 years that they've become much more sophisticated. I assume that a lot of you are familiar with the studio concept we have at SOM, which is that within the context of this 900-person office, we have 13 studios. And each of these studios is essentially like a small office that supports its own work. We do perhaps 4, maybe 5 projects simultaneously within the studio. And this work is all-inclusive. In other words, we begin the programming, design, and proceed all the way through working drawings in the same studio. So there's not a separate design and drafting department. So the philosophy is that everyone hired within SOM to do architectural work is in fact an architect. We do not hire separate draftsmen, for example, to do production work. Likewise, one of the technical resource areas of which we are most proud is the computer group. And they have a similar philosophy, which is that in order to work with architects, you really need to think like an architect. And to that end, virtually all of the people within the computer group are trained as architects. And the person tonight, Tony Mirante, who is going to be giving the lecture on our current computer capabilities in the office, follows that same mode. Tony was educated at Berkeley and received his Bachelor's of Architecture degree in 1979. Since then, he's in fact worked at several architectural firms in San Francisco prior to coming to SOM. And in 1979, upon graduation, he came and he's been working with our computer group since then. I think you'll find a lot of the work that Tony and the group is doing is very, very fascinating. It doesn't mean that you necessarily have to stop learning to draw, but I think that there are a lot of revolutionary things that's happening in the design process because of the computer. The revolutionary aspects are not in the way you think as an architect, but more in the way that you use technology as a tool to assist you in the design process. And so it gives me great pleasure to introduce Tony Mirante from our SOM computer group.
Although computers are capable of such realistic and complex renders, these images currently require expensive equipment.
I've never used one of these before. I'm sort of used to shouting at my audience. It gives me a feeling of command. How's that? How am I doing, okay? Craig asked me to talk a little bit about my experience. Briefly as I can put it, I guess I could say that I decided I wanted to be an architect when I was 12 and decided I didn't want to be one when I was 21. That came about my third year in school. I was fortunate in the sense that Berkeley offered a liberal arts program, and I split my last 2 years between economics and computer science, not really knowing which direction I'd take. I worked, actually after my first year and a half of school, I quit school because I didn't really think I was getting a real good feeling of what architecture was all about. So I went and worked for 3 firms at that time, and I worked for actually one firm all the way up until I graduated.
The time of day, seasonal changes may also be represented.
That is an introduction. I think that we're ready to start.
From spring to fall, a simple color.
Okay.
These are real places in our own time. Sometimes past, but these times really not free. Future times such as this proposed building are facilitated by computers.
Jerry, is the second projector plugged in? Doesn't seem to be.
Need not be confined to this world. This computer image is important for translucency, refraction, reflection, shade, pattern. The remainder of this presentation is about SOM. All the computer images you'll see, including the title, are done by SOM people on SOM hardware. All the programs described here were written here, not for architects and engineers, but by architects and engineers. There were 7 applications.
Okay, Jerry, why don't you bring them back about the beginning? We'll turn them off, starting with the bottom one.
This is our system. This is the way we use it. Since 1977, SOM...
Okay, turn the bottom one on.
New 1,700 square foot computer facility in Chicago has been filed with computers.
I guess I'm probably having trouble with that one. Why don't you reverse that one to the start?
1,500 tapes. SOM's magnetic spotting system is well lined at 40 inches per second. And the average is 1,000.
Are they both back at the start?
Over 100 graphic and non-graphic terminals are connected to high-speed dial-in lines to by computers.
Jerry, are they both back at the start? Okay, why don't you turn both of the projectors off, please? Now, turn them on, starting with the bottom one.
Computer usage within the firm is fairly well distributed between the engineering and architectural
Pardon me?
disciplines, as shown in the center.
Okay.
Computers at SOM are viewed as a workbench. All disciplines in studios are mechanical engineering.
They were just working a second ago. Why don't you plug the...
Computers in the same terminal. This enables the computers to be interconnected in a network that can be expanded or contracted in accordance with
Jerry?
the
Are they both attached in the back?
hardware and in all hardware. No functionality is lost by changing the number of functions.
How about in the back of the machine? Mine's not working at all. It's not doing anything.
From the accounting system, manpower projection system to develop graphically display manpower requirements. General purpose CPM programs often involve system scheduling from control.
Probably stood on it. Well, so So this is one. Okay. Jerry, set them both back to the beginning now. Okay, I think I've got it now. Okay.
SOM developed their own computer graphic system, 3D and interactive. Following features will illustrate how using the system will actually instruction. This is the origin of it. Then we begin to build elements. These elements are repeated. The element groups. Rotated.
All the images just shown here were completely generated by computers. All the images just shown here were completely designed by people. Computers and designers do very different things, but the former in the hands of the latter can be one of the most powerful tools. Computers can and should be thought of as a new and different kind of pencil. The quality of design produced with that pencil is entirely dependent on the talent of the user. This discussion is not one of computers as designers, but one of computers in design. The UNIVAC 1 was the first commercially available computer. In 1957, it cost $5 million and was 10 times slower than the programmable handheld calculators of today. The UNIVAC 9400 was one of the first of the second generation computers. It employed transistors instead of tubes and used high-speed disks and drums similar to those used today. It had 100 times the power of the UNIVAC 1 at 1/5 the cost. The IBM 360 computer, introduced in 1965, was one of the first of the third generation. Individual transistors used by the second generation to replace tubes were now replaced by integrated circuits. The decrease in component size from the tube, which was required to store a single bit of information, to the chip, which is a complete microprocessor, has been accomplished in only 30 years. The next 30 years should show similar advances. Computer hardware available to display visual images comes in a variety of sizes and shapes. These are called storage tubes. These are what we use primarily at SOM. They can be thought of a lot like a blackboard in that once you draw a line, to redraw the line, you have to erase the whole screen. The advantage of this system is that they're fairly inexpensive and they have a very high resolution. This is an example of a dynamic refresh screen. This screen gives you the ability to rotate elements without clearing the whole screen. You can also selectively erase on the screen. Disadvantage of the system right now is that it's very expensive.
It can also be used later on as working drawings.
This is an example of a color raster device.
There are some questions.
It's pretty much agreed that this is the way computer graphics is going to go in the future. It can be thought of just like a color TV set. The problem with the system right now is it gives a very low resolution and, again, it's very expensive.
6 o'clock at night. See how it's going to actually affect this building.
This is SOM's first plotter, plotted at 4 inches per second. These are flat-glared plotters. We actually employ the plotter in the upper left-hand corner of the slide. This plotter works on Sawyer's principle. That is, there's no moving parts in the head. The head actually sits on a cushion of air. This is an electrostatic printer. It gives output very similar to that which you get in a Xerox machine. This is an inkjet printer. The inkjet printer actually sprays ink onto the surface. For those designers who dislike the traditional interaction with screens and plotters, a variety of approaches have been proposed. This device throws the image into the room that you're viewing. So by moving your head, you can actually see how the image rotates in space. These are plasma screens. Their main advantage is that the screen itself is only about 1 inch deep, so that the screen can actually cover a whole wall surface. MIT's approach to computer graphics is a little different. They've chosen to use a backlit screen, which requires that you use approximately 2,000 square feet behind that screen to light it. It also requires that you have to mutilate an image chair. These and other tools of computer data design are here. They exist not only in university and research labs, but at SOM and other real-world organizations. They have been used in a variety of industry for years, and all indications are that CAD will be one of the most explosive growth areas in the 1980s. The aircraft industry has been a pioneer in applying computer and computer graphics to design. Since the early 60s, computers have been used to aid in the functional layout and the engineering of many aircraft. The F-16 fighter plane was totally designed on the computer. Structural engineers make effective use of computer graphics to easily display system and element performance under stress. High-stress components, such as turbocharger blades, are much more easily analyzed using computer aids.
This is an example of an interior study using these techniques.
The automobile industry uses computers from the design and engineering phase to the actual manufacture of the cars.
Then all the shadows generated.
Computer description of a car body is used to actually cut a full-scale model.
And we also have the ability to
Computer simulation of filling car trunks has replaced the need for expensive full-scale mock-ups.
of the building. This is for the entire day. Or we can isolate in.
Today, computers can convert the images used to design an automobile into instructions to control robots for actual assembly and welding of that automobile.
Has found application as powerful data display techniques.
Computer-aided drafting systems have been applied to many disciplines of the design industry. In addition to the familiar mechanical output, a variety of fonts and patterns can be produced by the computer.
Purely graphic means. Doors, windows, and
Computer-aided drafting can be effectively applied to many design disciplines. Elevations and floor plans are only one way that computer graphics may be used. Automatic generation of schedules and interior perspectives on production documents is greatly facilitated by computers. Computer-driven plotting devices can produce accurate, high-quality drawings. Axons, isometrics, and perspectives may also be produced using computer-aided drafting systems.
structural analysis systems in existence.
The production of highly complex engineering drawings may be simplified using computers.
Generated in 30 minutes. When originally done by hand, it took 3.5 weeks.
Electrical engineers have taken advantage of computer-aided drafting in many aspects of their profession, from laying out distribution systems to complex integrated circuits.
Records to shapes of structural systems can automatically be displayed and stored using the system.
Computer graphics has shown itself to be extremely effective in the display and presentation of all kinds of data.
Inherent within the structure.
Numeric information combined with graphic maps can convey large amounts of information at a glance.
Defines the structure.
Charts and graphs may be much more effectively generated by computers than by manual methods.
Generate a complete structural model. This is a model of the hive tent. First, the circle of nodes is defined.
Computer-aided animation and simulation have demonstrated that computers are capable of generating amazingly sophisticated imagery,
Outside corners are specified.
including completely machine-drawn cartoons.
Tenor input. The finite elements for each decider. Data required to completely define this tent is shown here in its entirety.
Computers can smooth faceted surfaces into continuous ones, such as this mask of Peter Fonda.
Pylons used to support this tent are then defined. Beams and supporting cables are then added.
Although computers are capable of such realistic and complex imagery, these images currently require expensive equipment and large amounts of time.
Using the structural system, it's possible to design individual members and select sections. Sharing moment diagrams may also be produced.
Computer simulation of the actual in-flight experience has gotten to the point that the FAA will grant 1 hour of flight time for every hour spent in a simulator. I was told by a salesman recently that there are pilots that fly DC-9s who, the first time that they take off, is with the passengers.
Contouring capability is also directly applicable to civil engineering. This is a computer-drawn map of the Mecca University campus.
Night, day, and weather conditions are simple color changes to existing images.
The fragment site was automatically defined as defining sections.
The time of day and seasonal changes may also be represented by color changes.
Two sections are then smooth and meshes and codes. Contours then are automatically generated using simple commands.
Again, to change from spring to fall is a simple color change.
Indicate the direction of flow. The magnitude
Images of real places in our own time
may be displayed with a raster image where the bright colors highlight the steeper incline.
or times past, such as Times Square in 1930. Our future times, such as this proposed building, are facilitated by computers. Computer simulations need not be confined to this world.
Areas may be displayed on the engineer's terminal. Roads and other site work may be interactively designed.
This computer image is important because it shows transparency, translucency, refraction, reflection, shade, shadow, and texture. The remainder of this presentation is about SOM. All the computer images you will see, including the titles, were done by SOM people on SOM hardware. All the programs described here were written here, not for architects and engineers, but by architects and engineers. Of the 7 application programmers in Chicago, all have at least 1 degree in architecture, most have 2. This is our system, and this is the way we use it. Since 1977, SOM's computer capability has increased many-fold. The new 1,700 square foot computer facility in Chicago houses 5 complete computers. This includes 5 printers, 2 billion characters of disk storage, and 1,500 tapes.
The new design rows may be put back in the database for automatic generation of final content.
SOM's Dianetic plotting system can draw lines at 40 inches per second and can be accurate to 1/1000th of an
Electrical
inch.
engineering design performance specifications have also been made interactive with SOM computer systems.
Over 100 graphic and non-graphic terminals are connected through high-speed or dial-up lines to the 5 computers.
The mechanical engineer's design process has been enhanced using these interactive techniques. entire design can be performed using computers from initial layout to working drawing.
Computer usage within the firm is fairly well distributed between the engineering and architectural disciplines, as shown in the center pie graph.
From this data line layout, information
Computers at SOM are viewed as a workbench. All disciplines in a studio, from mechanical engineering to architectural design, use the same computers and the same terminals. This enables the computers to be interconnected in a network that can be expanded or contracted in accordance to the needs of the firm. Since all software runs on all hardware, no functionality is lost by change in the number of functioning computers.
you mentioned earlier on, one of the views of the system is that
Computers have long been used for accounting and management at SOM. In addition to the project management reports from the accounting system, a manpower projection system has been developed to graphically display manpower requirements.
first is basic, defined by the architect.
A general-purpose CPM program has also been developed to assist in scheduling and project control.
Now the interior people use that same data.
Planners use the system to determine how many bonuses their particular building may be granted by city planning. These bonuses include setback at the base,
And we can generate room schedules.
reduced floor area in the upper
Managers
portion,
by laying out their plans. Single objects can be clipped
in atrium spaces. And this information can be
One magnificent
tabulated in a
project
report.
in Michigan note made use of the computer in many ways just discussed.
SOM has developed their own computer graphic system. It's 3D and interactive. The following sequence will illustrate how a user on the system will actually construct an image.
The project from the hand.
First, the origin is located. Then we begin to build elements. These elements are repeated.
View from the proposed building down Michigan Avenue.
Some of the elements are grouped
We designed the elevators for the building.
and rotated.
Did the structural analysis.
Others are moved.
And we can
Because
do-
the system is
There's something
3D, we
said
can
by
flip
this
into
plan
perspective.
that Our building was block field at 8 feet. That it proves that was
Extrude elements.
the solar state. Now the information from this solar state has already been used before. You've seen it. Instead of viewing it in perspective now, we're simply viewing it as graphic. We can watch
An axionometric view is taken.
during the course of the day.
Elements can be clipped. Curves may be introduced. Orthographic views may be taken at any time. Whole groups may be repeated. Elements can be regrouped and repeated. And any number of views may be taken. Any desired level of detail may be added. Several cityscapes have been built up using this technique, including Chicago, Here's a view looking down the river. A view down Michigan Avenue. Hartford. Indianapolis. Houston. in Hong Kong. One of the important benefits about using computers in design is the fact that using a computer as a tool, you can take advantage of redundant information. That is, information used to create perspective or massing drawings can also be used later on as working drawings. This is another example how the redundant information is used. There is some question whether the atrium of the building in the right would be blocked by the sun. We felt that it would be, and to prove it, we used the computer. Computer eye now will actually be looking from the sun's position, and we're going to go from 7 a.m. up to 6 o'clock at night to see how the sun actually affects this building. And in fact, the solar study proved that the atrium would be blocked by the sun for a good portion of the day. Following sequence will illustrate how a complex facade can be easily drawn using the graphic system. First, we're going to identify a particular unit in a window wall, build that unit up, and then begin grouping these elements to repeat them. Once repeated, then we can step back a bit and take a look at the elevation of the building. At this point, we can add on greater detail. Flip into perspective and take a look at how this building looks in 3D. Facades and massing of the Irving Trust project by the New York office were built up to create this image. Notice that the computer has removed all the hidden lines. Hidden line removal is a process by which the computer will identify those lines or portion of lines that can be seen or would be hidden if the object were solid. This series of cubes will illustrate uses for this technique. First, hidden lines are removed. And then, taking advantage of our raster device, we can actually apply tones to this image. We can get a very realistic feel. This is an example of an interior study using these techniques. First, hidden lines are removed. Then all the shadows generated by the sun during the day can be simultaneously displayed. And we also have the ability to get into that space and see how that shade patterns will affect the interior of the building. Now this, of course, is for the entire day, or we can isolate in on one particular moment. The graphic system has found application as a powerful data display technique. Data pertaining to the contents and finishes of a building can be graphically coordinated with the building plan. A specific room may be selected by purely graphic means. Doors, windows, and furniture may be called up from the database. Furniture and window labels may be included. Data associated with room, name, title, phone number may be displayed. Data can be edited and replaced in the database. Reports of the floor can be generated by room, summarizing furniture and finish. On a more pragmatic side, SOM has developed one of the most sophisticated building structural analysis systems in existence. The structural model for the Sears building can be completely generated in 30 minutes. When originally done by hand, it took 3.5 weeks. By hand being defined as actually manually punching cards. The selected shapes of structural systems can automatically be displayed and distorted using the system. Inherent within the structural system is the ability to define a pattern, which when repeated defines a structure. The system takes advantage of the sophisticated graphic techniques already discussed to generate a complete structural model. This is a model of the Hodge tent. First, the circles of nodes is defined. Then an inner circle. Outside corners are specified. Curvature of the edges of the tent are input. The finite elements for each side are defined. Data required to completely define this tent is shown here in its entirety. Pylons used to support the tent are then defined. Beams and supporting cables are then added. And the tent and the supporting structures are combined for the complete Hodge tent. Using the structural system, it's possible to design individual members and select sections. Shear and moment diagrams may also be produced. Because SDMS accesses the same graphic library as the rest of the SOM graphic systems, a dimensional perspective may be taken. Stresses on the matte foundation of this structure may be displayed as contours. Contouring capability is also directly applicable to civil engineering. This is a computer-drawn map of the Mecca University campus. The initial survey data describing the site was automatically refined into finer and finer sections. These sections are then smoothed and a mesh is imposed. Contours then are automatically generated using simple commands. From this, the computer can automatically generate a hydrology map where the arrows indicate the direction of slope. The magnitude of slopes, shown here, may be displayed with a raster image where the bright colors highlight the steeper inclines. The database describing the entire site may be subdivided into smaller areas for detailed design. These areas may be displayed on the engineer's terminal. Roads and other site work may be interactively designed. This is defining the baseline of a road, specifying the number of sections that you want off of that baseline. Once cut, individual sections may be selected for analysis and design. The computer itself provides a variety of interactive design aids. It can change scale automatically and identify points. A road template may be interactively designed. And plotted on working drawing sheets. The new design roads may be put back into the database for automatic generation of final contours. Electrical engineering design performance specifications have also been made interactive with SOM's computer system. The mechanical engineer's design process has been enhanced using these interactive techniques. The entire design can be performed using computers from initial layout through working drawings. First, the diffusers are added manually by the engineer. Then the engineer selects a single line layout. From this single line layout and the information the engineers have given about the diffusers, the computer will actually design the ducts and return the information in double line form. If needed, labels also may be added. And then we transmit that information to a working drawing. As I mentioned earlier on, one of the beauties of the system is that you can take advantage of redundant information. In a recent project, the King Abdul Aziz University made use of the computer capability to assist in the coordination and production of some of its working drawings. First, this base sheet defined by the architects. Column lines were laid out by the architects. Now, the interior people used that same data to overlay on their partitions. Once the partitions have been finished, then we can generate room schedules. Structural engineers took advantage of the system by laying out their pans. Single objects can be clipped and blown up for greater detail. One Magnificent Mile project at Michigan and Oak made use of the computer in many ways just discussed, including site plans, this is a view of the project from the Hancock Center. This is a view of the site from the lake. This is a view from the proposed building down Michigan Avenue. We designed the elevators for the building. Did the structural analysis. And even did a solar study. There was some concern by city planning that our building would block the Oak Street beach. So to prove that that wouldn't be the case, we did the solar study. Now the information from this solar study has already been used before. You've seen it. Instead of viewing it in perspective now, we're simply viewing it in orthographic. We can watch shadows traverse during the course of the day. particular building, and elevations. And that same information used for the elevations were used for site studies. The SOM computer group has made a contribution to the fine arts via Moreau. This is a new sculpture that just went in across from the Picasso. We were given a maquette that was 30 inches high. Our job was to model the maquette so we could design the steel for it. We also wanted to get full-size drawings to make sure that the maquette was actually blown up to scale. Our concern was that we didn't want to destroy the maquette because it in itself is very beautiful. So what we did first of all was to just place dots onto the maquette using an approach called dual digitizing. Then we took pictures of the maquette at 2 different angles. This allowed us to pick out 3-dimensional space from these 2-dimensional flat pictures. Unfortunately, our first attempt at this didn't really come out to be a very good representation. So one night we had to, at 2 o'clock in the morning, go down to a hospital and send it through a CAT scanner. It's actually the same process that you would use for a person. There's a computer which drives this X-ray machine, and every quarter inch a section was taken of the maquette. Now, the data that we got back from the hospital was a raster image. Unfortunately, it didn't interface very well to our system at that time. We didn't have raster capability. So we had to write an edge finding routine. Basically, this routine determined where the edge of the maquette actually was for each section. We came up with a very realistic image. What's been described here is a workbench, a tool. No attempt has been made at SOM to do automated design. The attempt, past, present, and future, is to build tools to assist and enhance the firm's most valuable and perhaps its only asset, its people. The computer is a tool, certainly a different one than those one might expect to find in a design environment, but a tool nonetheless. As with any tool, its effectiveness is dependent totally on the craftsmen who use it. I've attempted to survey what we do, how we do it, and touch upon why we might want to do these things. Now, let me give you a taste of what's possible in the future. Could you turn the movie on, please? Okay, I'm going to run the film backwards and I'll explain to you what you're seeing. It's a film done of Chicago. Now, the first structure we're going to be approaching is the structure that we're in right now. It's a 33 West Monroe project, structure coming off to your left right there. All the structures done by SOM will be delineated in white. Next to 33 West Monroe is 30 West Monroe, the Inland Steel Building. So we swing up over First National Plaza. This is a view of the building that we're just constructing, 3 First National. Terrace Bank. And the Sears Tower. Now we'll race down Wacker Drive. And we'll get a view of the new Hilton Hotel that we're just getting underway on. Okay, we've just crossed the river and we're going down Michigan Avenue now. Around the water tower. And this is a view from One Magnificent Mile. We're actually looking down the tube of the structure now, and the Hancock is to the left. Okay, thank you. That is the presentation. If you have any questions, I'll entertain them now. Are there any questions? Well, right now we have a very large amount of hardware. We're running 2 VAX 11780s. We have 2 PDP 1170s and an IBM System 34. The total of our hardware, I guess, expenditures after this year will be about $3 million. It's an excessive amount of money, it seems like, but we're supporting 2,200 people with that amount of money. Now, we're really the first experiment of this kind. No other architect's really gone into CAD the way we have. Actually, it's nothing that's been really unique to computers. The business firm did it about 10 years ago. They found out that computer people writing programs for business people didn't really succeed too well. It was only when business people wrote their own programs. Well, we're the first experiment of architects writing their own programs. So there's certain inefficiencies that we have to absorb in the cost. The cost of compute power is dropping dramatically. And what we're gearing for right now is to make our system economically viable for a 30-person firm. I don't think that that is really unrealistic right now. Certainly in 5 years it won't be any problem. Actually, the film was shot off an ENS system. We had this data, yeah, it was real time. We had this data built up in a database of Chicago. We brought our data to a filmmaker in Hollywood, and in a short period of time, it took us only 4 days to produce that film. Each image of the film was shot off an ENS system. What they do is they set a camera up in front of an ENS screen. That's the refresh raster device that I showed you at the beginning of the show. And they had a computer drive the camera. So they just went away for 2 days and they came back and their film was done. I'm not sure. I'll have to check. Well, I had the most amount of architectural experience and the least amount of computers. I went away with about 1.5 years in school. But it's not really important that you concentrate on computers. What's really important is that you have a knowledge of architecture. With that knowledge, there are a lot of people that are willing to train you in the use of computers. Computers itself, it's only a tool. When I first started at SOM, my programming experience wasn't enough really to warrant getting into actually a computer environment. But because the people I work with were willing to put up with me for a bit till my programming caught up, that wasn't really a problem. I think that that's basically true. You can get away actually probably with only a few classes in the computer science department, but concentrating most of your time in the architectural department. The slides that you saw in the beginning all came from vendors. And I went out with a vendor last week for lunch, and he told me that he feels, and his company feels, that the architectural market is going to be about 3 times greater than any other market that they have. So as soon as it breaks, as soon as architects get introduced into computers, then you're going to find that there's going to be a lot of job openings for architects with knowledge in computers.